A machine sits silent in the corner of a factory floor, untouched for 3 years. 17 technicians have declared it unfixable. The scanners show nothing wrong. The diagnostic computers report clean bills of health. The machine tells them what they want to hear. It lies. Because every time the press is loaded and brought to temperature, it drifts. The hydraulic arm loses its precision. The tolerances collapse. Production stops. The machine knows. The sensors do not. The veteran enters. He ignores the diagnostic cart wheeled beside him. He does not ask for the error logs. He walks to the machine and places his palm flat against the cold pump housing. He waits. He feels the metal. He closes his eyes. "It is not broken," he whispers. "It was born a liar." This is not a repair story. This is an autopsy of a deception written in steel. The hydraulic press arrives at the veteran's shop on a flatbed trailer, and it arrives with a reputation that precedes it like a funeral procession. 3 factories have returned it to the manufacturer. 2 senior engineers have quit their positions rather than continue wrestling with its ghost. The owner, a man named Castellanos, stands in the doorway of the veteran's workshop with the look of someone who has already spent his last dollar on hope. The machine is a 40-ton hydraulic stamping press, built by a reputable German firm, installed new just 4 years ago. On paper, it is flawless. In practice, it is a curse. Castellanos describes the pattern with the precision of a man who has memorized his own nightmare. The press works perfectly in controlled tests. Empty cycles run for hours without deviation. The hydraulic pressure holds steady. The servo motors respond with Swiss precision. But the moment the press is loaded with production work, the moment real steel is placed under real force, the machine begins to drift. Not immediately. Not in the first 10 minutes or the first 20. 40 minutes. Always 40 minutes. At the 40-minute mark, under sustained load, the hydraulic ram begins to lose its positional accuracy. The drift is small at first, barely 1/1000th of an inch. But in precision stamping, 1/1000th of an inch is the difference between a part that fits and a part that is scrap. Within an hour, the drift compounds. The press begins to wander. The safety sensors trip. Production halts. The veteran listens without interrupting. He has heard stories like this before, but never one so specific, never one so maddeningly consistent. Castellanos continues. The scanners report no faults. The pressure sensors read normal. The ECU log is spotless. The hydraulic fluid has been tested, replaced, tested again. The seals have been inspected under magnification. The servo controllers have been recalibrated to factory specifications. 17 technicians, 17 separate diagnostic sessions. Some lasted days. One lasted 3 weeks. All of them ended the same way. No fault found. Machine operates within parameters. Problem must be operator error or environmental factors. But Castellanos knows it is not operator error. He has run the press himself. He has watched it fail under his own hands. He has stood beside it and felt the moment when the machine stops obeying the laws of engineering and begins obeying something else. The veteran walks a slow circle around the press. It is a beautiful machine, all German efficiency and over-engineered precision. The frame is massive, cast iron painted industrial gray. The hydraulic pump sits low and compact, its housing machined to tolerances that would make a watchmaker weep. Everything about it screams quality. Everything about it screams reliability. Yet, it has destroyed the reputations of 17 professionals. The veteran stops walking. He stands in front of the pump housing and places both hands flat against the metal. It is cold. The machine has been off for hours, transported across the state, sitting idle on the trailer. He closes his eyes and listens to the silence. Castellanos watches him with the cautious hope of a man who no longer believes in miracles, but cannot afford to stop looking for them. "What year was it cast?" the veteran asks. Castellanos blinks. Of all the questions he expected, this was not one of them. The machine was installed in 2019. I would have to check the foundry records for the individual components. "Check them," the veteran says. His hands remain on the housing. "I need to know what year this iron was poured. I need to know what batch it came from." The machine was a masterpiece of German engineering, but it was speaking a language the 17 technicians couldn't translate. They had listened with their scanners, their sensors, their digital ears. But the metal was speaking in a tongue of expansion and contraction, of crystalline memory and foundry sin. The veteran knew that to catch a liar, you had to first learn its native dialect. While Castellano searches for the foundry paperwork, the veteran begins his examination. But he does not reach for tools. He does not connect diagnostic equipment. He walks to the machine and runs his hands along the pump housing, the hydraulic lines, the mounting brackets. He is reading the metal the way another man might read a book. Modern diagnostics depend on sensors that measure symptoms, not causes. A pressure transducer tells you the hydraulic pressure at a single point in time. A temperature probe tells you the heat of the fluid. A position encoder tells you where the RAM should be. But none of them tell you why the machine is lying. The veteran has seen this trap before. The digital readout is a translator. It can only report what it understands. It speaks the language of voltage and resistance, of binary states and threshold values. But metal speaks a different language. Metal speaks in expansion and contraction, in crystalline structure and grain boundaries, in the microscopic wars that happen between atoms when heat and pressure collide. The machine's ECU believes everything is normal because the sensors are telling the truth as they understand it. The pressure is within range. The temperature is acceptable. The position feedback matches the commanded position. But the metal itself is lying to the electronics. The housing is changing shape in ways too small for the sensors to detect, but large enough to destroy precision. The veteran explains this to Castellanos, who has returned with a thick binder of documentation. "Your scanners are not wrong," the veteran says. "They are simply blind to what matters. They measure the surface. I need to understand the depth." He opens the binder and begins searching through the procurement records, the material certifications, the foundry stamps. Most factory owners never look at these documents after installation. They trust the manufacturer. They trust the specifications. But the veteran knows that specifications are promises, and promises are only as good as the humans who make them. Castellanos watches as the veteran's finger traces down a column of batch numbers and dates. "What are you looking for?" "A discrepancy," the veteran says. "A moment when someone made a decision that seemed insignificant at the time." He finds it on page 47. A material certification for the pump housing. The specification calls for grade 40 gray cast iron, a standard material for hydraulic components. Strong, machinable, thermally stable. The certification confirms that the housing was cast from grade 40 iron. But there is a note in the margin, handwritten, barely legible. It says, "Batch 17 November mixed stock, chromium content plus 0.3%, approved for use." The veteran stares at that note for a long moment. Then he closes the binder and walks back to the machine. He places his hand on the pump housing again. This time, he is not feeling for texture or temperature. He is feeling for truth. "Run the machine," he says. "Empty cycle, no load. I need to watch it warm up." Castellanos powers on the press. The hydraulic pump engages with a smooth mechanical hum. The ram cycles up and down in perfect rhythm. The veteran stands with his palm pressed against the housing, his eyes closed, his breathing slow. 10 minutes pass. 20. 30. At 38 minutes, the veteran opens his eyes. "Stop the machine." Castellanos hits the emergency stop. The press falls silent. The veteran removes his hand from the housing and flexes his fingers. "The housing is expanding," he says. "Not much. Not enough for your sensors to flag, but enough to create drag on the internal piston. That drag forces the hydraulic system to compensate, which generates more heat, which accelerates the expansion. It is a feedback loop, and it is invisible to every diagnostic tool you own." Castellanos stares at him. "How can you know that from touching it?" "Because the metal told me," the veteran says. "It always does." The veteran explains his theory with the calm certainty of a man who has spent decades listening to metal confess its secrets. This is not a design flaw. This is not a manufacturing error in the traditional sense. This is a casting flaw, a birth defect written into the molecular structure of the iron itself during the pour. The note in the margin told him everything he needed to know. November 2017. Mixed stock. Chromium content elevated by 0.3%. Approved for use. Someone at the foundry made a decision. The scrap metal they received that month was not pure grade 40 stock. It contained a higher percentage of chromium than the specification allowed. Not much higher, just 0.3%. In the world of metallurgy, that is a rounding error. In the world of thermal expansion, it is a catastrophe waiting to happen. Castellanos listens, trying to follow the logic. But the housing passed inspection. It was certified. How can 0.3% matter? The veteran picks up a piece of chalk from the workbench and draws two parallel lines on the concrete floor. Imagine two railroad tracks, he says, both made of steel, both laid on the same day. But one track is made from steel with slightly more chromium. At room temperature, they are identical. You cannot tell them apart. They expand and contract at nearly the same rate. Nearly. He draws a sun above the lines. Now summer comes. The temperature rises. Both tracks expand. But the chromium-rich track expands at a slightly different rate. Not much. Maybe a few thousandths of an inch over 100 feet. But that difference is enough. The tracks buckle. The train derails. Castellanos stares at the chalk lines. And the pump housing is the same? Exactly the same, the veteran says. Your housing was cast from two different melts. The bulk of it is standard grade 40 iron, but somewhere in that November batch, a portion of the pour contained the contaminated scrap. The foundry mixed it in, thinking the difference was within tolerance. And at room temperature, it is. The housing machines beautifully. It holds pressure perfectly. It passes every static test. He taps the chalk against the drawing. But when you run the machine under load, when the hydraulic pump generates sustained heat, the two different alloys begin to expand at different rates. The housing grows unevenly. The internal bore distorts by a few thousandths of an inch. Not enough to cause a catastrophic failure, not enough to trip a sensor, but enough to create friction on the piston, enough to generate drag, enough to make the machine drift. The veteran stands and brushes the chalk dust from his hands. The machine was born with two materials fighting each other, and no blueprint, no diagnostic computer, no pressure sensor could have predicted it. Because the flaw is not in how the machine was built. The flaw is in what it was built from. Castellanos sits down heavily on a workbench. He has spent a small fortune chasing ghosts. He has watched 17 professionals walk away in defeat, and the answer was written in a margin note that no one thought to read. Can it be fixed? He asks. The veteran nods slowly. It can be fixed, but not by replacing sensors, not by recalibrating controllers. We need to address the housing itself. We need to compensate for the expansion that the foundry built into the metal. The chalk lines on the floor explained the physics, but they didn't explain the guilt. For that, he needed a voice from a foundry that no longer existed. The veteran does not trust his own theory until he can prove it with institutional memory. Theory is cheap. Speculation costs nothing. But the truth lives in the records of the men who poured the iron, and most of those men are retired or dead. He makes a phone call. The number belongs to a man named Harlan, a foundry worker the veteran knew 30 years ago when they both worked the night shift at a casting plant in Pennsylvania. Harlan is 73 now, living on a fixed income in a town that no longer has a foundry. But his memory is sharp, and he spent 40 years watching molten iron flow into molds. The phone rings 4 times before Harlan answers. His voice is rough, scarred by decades of breathing foundry dust. Harlan, the veteran says, I need you to remember something. November 2017. A batch of hydraulic pump housings, grade 40 gray iron. There was a contamination issue. Chromium content ran high. There is a long silence on the other end of the line. The veteran can hear the television in the background, the sound of a game show host announcing prizes that no one will ever win. Then Harlan speaks, and his voice is changed. The roughness is gone. In its place is something colder, something that sounds like guilt. That was the November batch, Harlan says quietly. We knew. The veteran closes his eyes. He knew the answer before he called, but hearing it confirmed still feels like a punch to the chest. Tell me, the veteran says. Harlan takes a breath. The story comes out slowly, like a confession that has been waiting decades to be spoken. In November 2017, the foundry received a shipment of recycled scrap metal from a demolition yard. The paperwork said it was clean, grade 40 stock, suitable for hydraulic components. But the paperwork was wrong. The scrap came from an industrial facility that had used chromium-enriched alloys for corrosion resistance. When the scrap was melted down and tested, The chromium content came back 0.3% over specification. The foundry supervisor made a decision. The difference was small. The tolerance was tight, but not impossible. The chromium would make the iron slightly harder, slightly more wear-resistant. It might even be an improvement. He approved the batch for use. 50 pump housings were cast from that contaminated melt. Most of them were fine. The chromium was distributed evenly enough that the thermal expansion remained predictable. But 3 housings had critical components cast from the heaviest concentration of the contaminated pore. 3 housings where the chromium content spiked high enough to create a measurable difference in expansion rates. Harlan remembers because one of those 3 housings killed a man in 1991. A hydraulic press in a Michigan factory exploded during a production run. The investigation found metal fatigue, thermal stress, a catastrophic failure of the pump housing. The company settled with the family quietly. The foundry scrapped the batch records. No recall was ever issued. We were told to forget it, Harlan says. The lawyers made it go away. But I never forgot. I knew there were 2 more housings out there. I knew they were ticking bombs. I just didn't know where they went. The veteran opens his eyes. He is standing in front of the press, staring at the pump housing that has destroyed 17 careers. One of them is in my shop right now, he says. Harlan is silent for a long moment. When he speaks again, his voice is barely a whisper. I'm sorry. It's not your fault, the veteran says. You were following orders. That doesn't make it right. No, the veteran agrees. It doesn't. He thanks Harlan and ends the call. Castellanos has been listening from across the shop, his face pale. There are 2 more of these machines out there? There were, the veteran says. One killed a man 33 years ago. The other is probably sitting in a warehouse somewhere, waiting for someone to make the same mistake you did. Castellanos looks at the press with new eyes, as if seeing it for the first time. This isn't a machine, he says. It's a cover-up. It's both, the veteran says, and now we fix it. The veteran refuses to rely on theory alone. He needs to feel the expansion with his own hands, to confirm what the foundry records and Harlan's confession have told him. He needs to stand beside the machine as it transforms from cold iron into a living, breathing thing that fights against its own design. He instructs Castellanos to run the press through a full production cycle. Not an empty test, not a controlled diagnostic, a real stamping operation with real steel under real force. Castellanos loads a blank into the press bed. The veteran positions himself beside the pump housing, his palm pressed flat against the cold metal. The press engages. The hydraulic pump roars to life. The ram descends with the force of 40 tons, crushing the steel blank into shape. The cycle repeats. Again. Again. The rhythm is hypnotic, the sound of industry doing what it was designed to do. The veteran stands motionless. His hand remains on the housing. His eyes are closed. He is listening to the metal speak. 10 minutes pass. The housing is warm now, heated by the friction of the hydraulic fluid moving through the pump at high pressure. 15 minutes. 20. The warmth becomes heat. The veteran can feel it radiating through his palm, soaking into his skin. At minute 38, he feels it. A barely perceptible tightness in the metal, like a joint swelling under strain. The housing is no longer a static object. It is moving, growing, expanding in ways that no sensor can detect because the change is too small, too gradual, too perfectly synchronized with the heating cycle. He opens his eyes and looks at Castellanos. The housing is choking the piston, he says. His voice is calm, but there is an edge of certainty in it that was not there before. Not enough to seize, not enough to stop the machine, but enough to create drag, enough to force the hydraulic system to compensate. That compensation generates more heat. The heat accelerates the expansion. It is a feedback loop that begins at 40 minutes and compounds until the drift becomes catastrophic. Castellanos watches the press continue its cycle. The ram moves up and down with mechanical precision. To his eyes, nothing has changed. But the veteran sees what the sensors cannot. He sees the metal betraying itself. The veteran retrieves a micrometer from his toolbox, a precision measuring instrument capable of reading to 10,000ths of an inch. He measures the outer diameter of the pump housing at room temperature, recording the number in a small notebook. Then he waits. The press continues running. 30 minutes. 40. 50. At the 1 hour mark, he stops the machine and measures again. The difference is invisible to the naked eye, but the micrometer does not lie. The housing has expanded by 0.003 of an inch, 0.003 inches, a distance smaller than a human hair, a distance that would be meaningless in almost any other context. But in a precision hydraulic pump, it is catastrophic. The internal bore has distorted just enough to create friction on the piston. The piston drags against the housing wall. The hydraulic pressure spikes to overcome the resistance. The control system interprets the spike as normal operational variance and adjusts. But the adjustment is wrong because the assumption is wrong. The system believes the housing is stable. The system believes the geometry is constant. The metal knows better. The veteran explains that a modern engineer would replace the entire pump assembly. A new housing, machined to perfect specifications, shipped from Germany with a lead time of 16 weeks and a price tag of $60,000. It is the textbook solution. It is also unnecessary. The veteran remembers a different era, before just-in-time manufacturing and computerized inventory systems, when machinists kept drawers full of shims and spacers for exactly this kind of problem. When a component did not fit quite right, you did not order a new one. You made it fit. You compensated. You adapted. He retrieves his notebook and begins calculating. The expansion rate of the contaminated housing is consistent. 0.003 of an inch at operating temperature. The expansion is radial, meaning the internal bore grows uniformly in all directions. If he can pre-compensate for that growth, if he can reduce the bore diameter by the exact amount it will expand, the piston will operate in a stable geometry regardless of temperature. The solution is a sleeve. A custom-machined insert that fits inside the pump housing, made from an alloy with a stable thermal expansion coefficient. The sleeve will act as a new bore surface, one that does not grow when heated. The contaminated housing will still expand, but the expansion will be absorbed by the gap between the housing and the sleeve. The piston will only contact the stable sleeve surface. Castellanos watches as the veteran sketches the design on a piece of paper. You are going to machine a part that compensates for a birth defect? I am going to give the machine what it should have had from the beginning, the veteran says, a housing that does not lie. He takes precise measurements of the internal bore, accounting for the wear patterns created by 3 years of operation. He calculates the wall thickness needed for the sleeve to withstand 40 tons of hydraulic pressure without deforming. He selects an alloy, a nickel-steel blend used in aerospace applications, known for its thermal stability and resistance to fatigue. The raw material costs $140. The veteran machines it himself on a manual lathe in his shop, working slowly, checking his measurements after every pass of the cutting tool. The work takes 4 hours. No computer controls, no CNC precision, just a man, a lathe, and the knowledge earned from 40 years of making metal obey. When the sleeve is finished, it is a thing of beauty. The surface is mirror smooth. The dimensions are exact, to within 0.005 of an inch. The veteran slides it into the pump housing, and it fits perfectly. A mechanical kiss between old iron and new steel. He reassembles the pump, reconnects the hydraulic lines, and instructs Castellanos to run a full production cycle. 1 hour. 2 hours. The press stamps steel with relentless rhythm. The veteran stands beside it, his hand on the housing, feeling the heat build. But this time, the tightness does not come. The expansion happens, but it is absorbed harmlessly into the gap. The piston glides smoothly against the stable sleeve. The drift never appears. Castellanos stops the machine after 90 minutes and checks the stamped parts. Every dimension is perfect. Every tolerance is held. The press is no longer drifting. It is no longer fighting itself. He turns to the veteran with disbelief written across his face. You fixed a birth defect with a sleeve? The veteran corrects him gently. I fixed it with institutional memory. The sleeve is just steel. The machine was cured, but the veteran felt no triumph. As he watched the ram cycle with mechanical precision, he realized this victory was a hollow one. The press hummed with a new honesty, but the industry that created its defect was still sick. He stood in the hum of the workshop, feeling the weight of a knowledge that was dying with his generation. The veteran does not celebrate the repair. He stands beside the press as it runs, listening to the steady rhythm of metal shaping metal, and he feels something heavier than satisfaction. He feels the weight of what was lost. Modern diagnostics are designed for designed failures. A sensor can tell you when a part is broken. It can flag a voltage drop, a pressure spike, a temperature threshold exceeded. But it cannot tell you when a part was never right to begin with. It cannot read the history written into the crystalline structure of iron. It cannot see the decision made in a foundry 30 years ago when someone approved contaminated scrap because the difference seemed insignificant. The veteran reflects on this as Castellanos watches the press work. 17 technicians failed, not because they lacked skill, but because they trusted the tools more than they trusted the metal. They connected scanners and read clean reports and concluded that the problem must be elsewhere. Operator error, environmental factors, bad luck. But the metal was screaming the truth the entire time. It was expanding. It was fighting itself. It was dying slowly under the weight of its own birth defect. And no sensor could hear it because sensors only measure what they are programmed to understand. The veteran describes the erosion of institutional memory. The foundry workers who knew about the contaminated batch are retired or dead. Harlan is 73 and living on a pension that barely covers his medication. The engineers who designed the press never touched the pour. The technicians who serviced it never saw the line. The machine became a ghost because the people who could have identified it were gone. Castellanos asks the question that has been building in his mind since the sleeve was installed. How many more machines like this are out there? The veteran does not answer immediately. He knows the answer, but speaking it aloud makes it real. Hundreds, he finally says. Maybe thousands. Every time a foundry cuts corners, every time a supervisor approves mixed stock because the difference is within tolerance, another birth defect is born. Most of them never cause problems. The contamination is distributed evenly enough that the expansion remains predictable. But some of them, the ones where the chemistry spiked at just the wrong moment, those machines are out there right now, sitting in factories, waiting. Castellanos looks at the press with new eyes. Waiting for what? Waiting for someone to remember, the veteran says. Waiting for someone who understands that the scanner is not the oracle. It is just a tool. And tools are only as good as the wisdom of the person holding them. He does not celebrate because there is nothing to celebrate. He has saved one machine. He has proven that institutional memory still has value in a world that worships digital certainty. But he knows that for every machine he saves, 10 more will fail because the men who could have diagnosed them are gone. The knowledge is dying. The foundries are closing. The veterans are retiring. The machine hums, flawless now, its birth defect compensated by a sleeve that costs less than a diagnostic session. But the silence in the room is heavier than before. It is the silence of a truth that no one wants to hear. The age of institutional memory is ending, and when it ends, the ghosts will multiply. He didn't look back as he left the factory floor. He didn't need to. The steel had already said its piece. The veteran walks away, leaving Castellanos with a single piece of advice. Keep the sleeve. When I am gone, you will need to remember why it is there. Subscribe to the Forgotten Manual. The steel remembers, even when we forget.